So hello everyone again and welcome to my channel. So in here we'll be looking at the pericyclic reaction, and pericyclic reaction is quite interesting because this is kind of the movement of electrons in form of a circle. They are moving from one particular point between two carbons to another point between two carbons, and sometimes this involves between species or within a particular species. So one of these particular circles you need to be familiar with is where we have the presence of double bonds, and when you have the presence of double bonds in form of a conjugating system where in between double bonds you have sigma bonds here and there, this will enhance the process of this particular pericyclic reaction. One other important information you need to note is that you're not forming any intermediate, so there is no intermediate in this process, and this intermediate they are not going to be formed shows that there will be no form of any positive charge or negative charge or any radical being formed during this particular process in that particular intermediate. Now, one particular form of pericyclic reaction you're going to be focusing on today in this particular video is called the Diels-Alder reaction, and this Diels-Alder reaction is pretty much a particular type of cycloaddition reaction, and in here the particular form we're going to be looking at is just between two species, and one species you're going to be familiar with is either a diene or a dienophile. In our next video we'll be looking more on what dienes actually their purpose are in this reaction, and also we addressing dienophiles as well, but you just need to know these two species because they are really important in this particular cycloaddition reaction. Now, this reaction needs to be facilitated in the presence of heat, and heat is really important in this reaction, and this shows how thermodynamically favorable this reaction needs to undergo in terms of the presence of heat. And this heat is really important because they lead to transformation of various species from either trans to cis, and this really important in order for we to be able to facilitate the process of this reaction forming our final product. Now, one another important thing you need to note is that there is a change in the number of bonds that we have over here, or the appearance of pi bonds versus sigma bonds. So one important thing is that two pi bonds are really sacrificed, I must say, and these two pi bonds sacrification, I would say, leads to the formation of two sigma bonds. And since you know that sigma bonds, they are really energy important because they need more energy to form sigma bonds. Pi bonds require less energy for you to form them, thereby you need energy to put into the system for you to make. It's something that is really cost expensive, which is sigma bonds. So now when we look at the diene and dienophile, an example of this particular process is our diene, which has pretty much two pi bonds, and on the other side we have our dienophile, which we have over here with just one double bond, between the two carbons. In this particular species or region within this particular species is pretty much known to be an electron withdrawing group. So if you have an electron withdrawing group, what happens here is that there will be equal pooling of electrons in this particular region, making this to be much more electron deficient, which requires electron in this part, or wanting electron. Thereby this diene, what diene does is that it donates electron to the system, where the donation of electrons will lead to the formation of sigma bonds, which is kind of a delocalization of electrons over here and delocalization of electrons over there, thereby making this bond to break off, or the losing of our pi bond to form our sigma bond over here, and also the losing of our pi bond over here to form a sigma bond over here, and then the reforming of our pi bond over here in this region. So this is the delocalization of electrons over here, which is in a cycle that leads to the formation of our two sigma bonds by losing two pi bonds over there. Now this leads to the formation of our product, which we have over here, which forms a 6-membered ring region over here, and then we have our other segment, which we have over here. Now take note that this is our new sigma bond over here, and if you want to just be able to understand this clearly, just remember that 1 will interact with number 1 of the other species, and carbon 4 will interact with carbon 2 of the other species over here. So this will be our carbon 2, carbon 3 of our diene, and this will be our carbon 1 and carbon 2 of our dienophile. Now this reaction could actually go in the other way, in such a way that our movement of our arrows will be in the reverse direction. So what we have in this particular process is that we have our diene over here, and we have our dienophile over there, and it could actually go in the other way. These are double bond. So what happens in this particular case is that this arrow, instead of it going this way, could actually go this way, and this could go in this way, and this moving in that way. So instead of it going this way, it could go in the other way, and it still leads to the formation of our final product. Sorry, I have to cancel this arrow. It's actually going this way. So it's either you're going in the left side or you're going to the right side to form our final product. Now let's look at the MO, which is the molecular orbital theory, and how this will actually lead to the facilitation of our sigma bonds over here. One important thing is that for our diene over here, our diene mostly uses the HOMO, and because it's the HOMO, it donates electrons into the system because it has the highest occupied molecular orbital region. And since we are using butadiene over here, butadiene, which has a second phase over here, or a second form or possible molecular orbital that we use over here, is going to be placed at the top using its cis conformation. And since it's a double bond over here, all the coefficients are all the same over there. What we have is that we're going to have our node, because it has only one node, and once it has one node, now what we need to do is to make these two in phase and these two in phase, but these two over here to be out of phase with respect to each other. So this is what we have over there, and this is what we have over there. However, for our dienophile, which is electron deficient, what happens here is that we're going to have, and let me use this pen over here, our dienophile, where we'll be using the LUMO in this case, and our LUMO will be lacking electrons due to the electron radioion group regions, which is actually in this region over here. And the LUMO, since you're using two carbons in this region, then we'll be using the sigma 2 as well for two carbons. But in this case, what we have to do is that we'll have to make both of them to be out of phase with respect to each other. And now what happens then is that instead of we shading this region, we'll have to shade this region in such a way that this shaded region and this shaded region over here will overlap with each other, and this unshaded region over here and this unshaded region over here will overlap with each other. Therefore, this will lead to the formation of a sigma bond over here between carbon 4, which you have over here, and carbon 2 over there, and carbon 1 over here, and carbon 1 over here. So once you have this overlap, then you will actually facilitate the formation of a product in terms of the MO product, we're going to have this product over here, where this is our new pi bond over there, where both of them are in phase with respect to each other, which is actually a change because you are moving the arrows here to form a sigma bond over there, a pi bond over here, sorry. And on this side over here, we're going to have the big overlap. And what results in this place is that we're going to have shaded points over here, and this is the carbon 4 with respect to carbon 2, and on this other side over here we're going to have our orbital overlap, where this will be shaded and that will be shaded, and that will lead to the overlap between this carbon 1 and carbon 1 over there. And this is our final product, orbital, molecular orbital expression over there. Now the last important one is how will our transition state be formed. Now the transition state that will be formed is, one, it doesn't have any charge at all, no positive charge, no negative charge at all. What you have is just a delocalization of electrons, and this delocalization of electrons will really lead to the formation of a transition state, which will exhibit a chair conformation, because our final product leads to the formation of a 6-membered ring, and this our 6-membered ring needs a stabilization of its configuration, which is much more thermodynamically stable in the chair form. So what we have in this process is our transition state, where this is our diene, and this is our dienophile. And what happens here is that we're going to have our delocalization of electrons in here moving, because this is the disappearance of our pi bond over here, and this is the appearance of our sigma bond over here, and this is the disappearance of our pi bond over here, the appearance of our pi bond over here, disappearance of our pi bond over here, and the appearance of our sigma bond over here. Thereby this is our chair form, where this is our carbon bonds over there, and there is no charge in this transition state. And this results in the formation of our final product, where the configuration has a cis hydrogen positioning with respect to this particular carbon atoms over here in our dienophile over there. So this is our new pi bond over there, and over here this is our dienophile, and in this region here our two hydrogens are actually pointing either up or down, and this is our final product over there. So the reason why our two hydrogens are actually pointing in the same direction is because of this particular process over here, because of this overlap over there, thereby causing the hydrogens to point in the same direction when you're forming our final product, and that is what we have over there. So next video we'll be talking more about this process and more about our diene and dienophile, and also we're talking more about the stereochemistry of our final product, and also the regioselectivity of our final product as well, as this is mainly involved in the Diels-Alder reaction. All the same, thanks for watching. Please don't forget to hit the like button, share and subscribe, and let me hear your thoughts about this particular topic. Did you understand it? Hit a comment down below and let me hear your thoughts. All the same, have a good day. Peace, love you all, and see ya on my next video. Be smart.